Well, it's a pleasure to introduce Dmitry Kerner. He is from Ben-Gurion University of Negev. We will talk about fast cycles on perturbations of weighted-homogeneous germ. Thank you very much, Dmitry, for accepting the invitation. And you can start when you are ready.
Thank you very much. It's always a pleasure, yes, to speak in this seminar, especially when I managed to avoid all the software problems. But hopefully you see the presentation. So I will give this talk. About 1 year ago, I gave a talk in Brazilian seminar on a related subject, but then I was more interested in inner metrically conical germs, mostly surfaces. Now I will.
But you won't use the same notations, right?
Well, I will recall the notations, and now I'm more interested in fast cycles, which is the simplest abstraction to being inner metrically conical. So first of all, I will recall the very classics, the conic metric theorem, yes, that, and then I will show how to detect fast cycles on weighted homogeneous germs. Yes, there is some very simple criterion, and surprisingly simple, I would say. It gives us a lot of exotic Lipschitz structures on subgerms. Yes, and then, of course, weighted homogeneous germs, they are rather particular, rather special. We would like to extend to some, at least semi-weighted homogeneous, yes, or maybe even some further perturbations of weighted homogeneous. And to do this, we need to deform some foliations. And maybe this is known, but somehow not to me. So we did this work, we established some result, and then surprisingly, as a byproduct, we managed to trivialize some families by differentiable blow analytic homeomorphism. Yes, so I will speak about this, and then eventually I will state the theorem in the general way, the general formulation. So let's start. X will be always a complex analytic germ of any dimension and codimension. And everybody knows the conic structure theorem of Milner, or maybe even before. Yeah, so every germ is homeomorphic to the cone over its link. This homeomorphism is non-embedded, and in most cases it is far from being differentiable. Yes, you cannot force it to be differentiable in whichever way. Even worse, usually it significantly distorts local distances. And so the weaker question is whether this homeomorphism can be chosen at least by Lipschitz. Yes, at least by Lipschitz, so that the metric does not explode at the origin. On the next slide, I will give precise definition, recall what means by Lipschitz. Yes, that here, let's see the simplest example, which will be prototypical during my talk. So the horn, yes, the basic simplest horn, beta horn, or the horn of vanishing speed beta. Yes, when beta is equals to 1, we have just the cone, as you see. And when beta is higher than 1, then we have the sharp, the sharp point. Yes, and of course these two creatures, they are homeomorphic, yes, but not Lipschitz homeomorphic. Yes, they are not inner Lipschitz equivalent. And this will be actually the prototypical example for the whole talk. We will detect such horns, yes, that cannot be shrunk in some sense.
I noticed that this is a real example, right?
Yeah. Currently,
this is a real example, not complex.
Yeah.
But you said that you will always speak about the complex things,
but mostly, yes. Yeah, during most of my talk, I will detect, I will consider complex analytic germs and will detect some complex analytic things. But for simplicity, this is the most simple childish example in R3. Yes, this is the simplest abstraction to Lipschitz equivalence. Yes, basically on the right, when we have the honest horn, not just a cone, we have a fast vanishing cycle. You see this horn, as we approach the origin, it vanishes at the speed higher than linear. Again, all this is sort of hand waving. I did not define anything yet. And this turns out to be the simplest abstraction to by Lipschitz equivalence. And one would like to detect such fast vanishing cycles. Yes, so a bit more precisely. So we have here something which is non-trivial on the link, and it vanishes at speed higher than linear. And the question is how to detect or how to forbid such fast cycles. What are the homotopy type? What are the vanishing rates? Yes, at which speed it collapses to the point. Okay, so and feel free to interrupt me at any place. Yeah, so let's recall by Lipschitz equivalence and inner metrically conical germs. So as previously, as I stated, X will be a complex analytic germ here, and then we have the inner metric on X. Yes, for any 2 points, we consider the length of the infimum of the length of all the passes. Yes, in completely classical way. And then once we have 2 germs with their matrices, yes, and suppose we have a map, then the map, the homeomorphism will be called by Lipschitz if it distorts the metric not too much in a controllable way. Yes, so for some constant, strictly positive constant, and once we fix this constant, it holds for any 2 points on X. Well, and fact, for the simplest horn of the previous slide, the 2 such horns are by Lipschitz equivalent if and only if their exponents coincide. Well, and X is called inner metrically conical if it is by Lipschitz equivalent to the cone over its link. Yes, if this conic structure map can be chosen by Lipschitz. Well, and just to add, we always speak about complex-analytic germs, or at least sub-analytic germs, and then this homeomorphism can be chosen sub-analytic. Well, some examples. So if a germ is already homogeneous, then it is, of course, a cone. Yes. Now, any complex curve germ is inner metrically conical. Yes, this is the very old result. So you can draw it like this, just the union of several cones. Now, and apparently people thought that many germs are inner metrically conical, but there was some explosion of results in around 2008. Yes, so among AK surface singularities, the only IMC is A1. And then if you consider surface singularities inside C3, yes, and which are weighted homogeneous, and if the 2 lowest weights differ, then X is not inner metrically conical. And then some culmination was the thin-thick decomposition for normal surface germs. So yes, these 3 authors, they did much more, of course. In particular, one little corollary was that a normal surface germ is inner metrically conical if and only if it has no thin parts. Then they gave an explicit algorithm to verify whether a normal surface germ is inner metrically conical. So you resolve it, you get the resolution graph, and then from the resolution graph you get all that you want. The only problem is that sometimes it's tricky to resolve a singularity. And also this was for 2 dimensions, of course. So in general, the question is, what are the obstructions for being inner metrically conical? Inner metrically conical, yes, in the most naive way, conical. These are the simplest germs from the metric point of view. And of course, one would like somehow to classify them to know what are the large collections of such inner metrically conical singularities. and it is not quite known until now. So the question is, what are the abstractions? Well, the first and simplest abstraction is fast vanishing cycle. Once again, if there are any questions, please do not hesitate. Wait, am I online? Yeah. Hopefully.
Just
Yes.
without, I would like just to emphasize something, that when we speak about homogeneous singularities, then all of them are metrically conical, because this homogeneous structure, that means the cis direction, brings you, just direct the cis direction, brings you the topological conical structure, and it brings you the metrically conical structure. Then to take the next step, the most simple after homogeneous, you have quasi-homogeneous, weighted homogeneous, where the topological conical structure is given by the also by the cis direction. But then there is a point. It gives you the topological conical structure. It doesn't bring you any metrically conical structure. Then this was our observation with Alexandre, right? That even if you go to the just a little bit more difficult than homogeneous, then you already have this abstraction. Thank you. And I'm sorry, I just wanted just to emphasize something that.
Good. Yes. So yes, and I guess in most of these papers, the first abstraction to being inner metrically conical were fast vanishing cycles. In fact, in most of the papers, I think they spoke about fast vanishing loops. Yes, in the dimension 1. So let's define this. Here is the link of our germ. Yes, the link is supposed to be a sphere or something lying inside the sphere, but in a pretty brute way, I rectified it to the plane. Sorry. Metrically, it is more or less the same. Yes, maybe the plane compactified by some point. And well, in general, on the link is topologically non-trivial. There are some cycles. The homology is non-zero. And then once we have the cycle, we can we can contract the link to the origin. As the link is contracted, the cycles also get contracted, and then we get such germs inside X. So once again, here is the homology of the link. Suppose we have found some cycle which is non-zero. Yes, then maybe it will contribute to the fast vanishing cycle. So you see here there are two scenarios. On the left, we have just a cone. We have a cycle that is shrunk at a linear speed. On the right, we have a horn. We have a cycle which is shrunk at the speed at least 2. Yes. For example, you can distinguish these two vanishing speeds by the tangent cone. Yes, the tangent cone to the horn will be half line. The tangent cone to the cone will be itself, the cone itself. So even the dimension is different. Yes, so this is the picture observation. Let's state all this more precisely. Yes, so we have here something which is non-shrinkable. Yes, non-shrinkable means you cannot shrink it inside each link. Well, so first of all, a subgerm of X is called thin if the real dimension of the subgerm is strictly bigger than the real dimension of the tangent cone. For example, as you see the horn, it pretends to be thin. Now, a neighborhood of the subgerm is called hornic if every arc inside this neighborhood is tangent to y. Yes, so you can imagine a line and a horn around it, or it could be, say, y is the whole plane, and then locally we have sort of family of horns, yes, covering it and containing it. And well, we would like to deform, of course, to deform all our germs. So we speak about homotopy. Yes, the hornic link homotopy, yes, of a subgerm is ordinary homotopy such that all the links are preserved. Links are sent to links. The distance to the origin is preserved as I stay here. And moreover, all this homotopy, it occurs inside the hornic neighborhood. Yeah, so we do not change the subgerm too much. Yes, do not perturb its tangent cone, let's say so. So this is the hornic link homotopy. And our first cycle is a cycle on the link, yes, link of y, such that the germ y is thin, yes, in the previous sense, and it admits no hornic link homotopy to a non-thin germ. So sometimes you could face a thin germ, but you could just shrink it to a line, yes, which is not interesting. What we want is that we have something essential. We cannot just shrink it to a line, as in the case of the horn. We cannot just shrink it to its tangent cone. And if the link is just a circle, then y will be called a fast loop. Yeah, so this is these are the definitions basically. Yes, the picture is very naive and very natural, and the main question will be how to detect such fast vanishing cycles efficiently. So maybe once again example. This is again a real analytic case. Yes, take the horn, beta horn, over a circle. Yes, with beta bigger than 1. It is a thin set because you have here a real analytic surface and its tangent cone will be just half line. So the dimensions do not match. Now, y is shrinkable to its tangent cone, of course, if you consider it as a subset of R3. But inside itself, it is not shrinkable. Even more, we could consider y inside R3 with erased positive half axis of z. Yes, you could erase it. Then y could be still shrinkable to a line, yes, in a link way. But this homotopy is non-hornic. This homotopy will essentially change the tangent cone. So you see, here is an example. You could have a link completely contractible to a point, so naively it contains no homologies. But from the Lipschitz point of view, it contains homologies. Yes, as we see here. And then a very simple lemma, an inner metric cone can have no fast cycles. With these definitions, yeah, so once we detect a fast cycle, this is an abstraction for a germ to be inner metrically conical. And to recall from the previous slide, any curved germ, yes, is inner metrically conical, so it has no fast cycles. And once again, the main question is how to detect the fast cycles, because in the complex case in higher dimensions, we cannot really visualize the germs. It is hard to see how it looks like. Well, and okay, let's start fast cycles on weighted homogeneous complete intersection. So here is a germ, weighted homogeneous, isolated complete intersection, singularity. Yes, here are the weights. I order them in the non-decreasing way, and it could happen that several first weights coincide. So therefore, I specify this. So you see here is this number R. It could be just 1, or it could be higher. It can happen that several first weights coincide. And let me state the very particular result. So the proposition in a very special case. So suppose the intersection of this germ with the hyperplane yes, where the variable of the lowest weight vanishes. Yes, we eliminate the lowest weight. Suppose this intersection has isolated singularity. I forgot to say the germ will be the germ X will be always of dimension complex dimension n, little n. And suppose omega 1 is smaller than omega n. Then X has a fast cycle of homotopy type, the wedge of spheres, as always. And its tangent cone will lie inside the half plane. Yes, in the first coordinate we have the half of the axis, and all the rest we have here x2 up to xr. Yes, in the same way as we split the weights. So this is the first part. Now we would like especially to know when the tangent cone is of dimension 1. So it is of dimension 1 if and only if omega 1 is strictly smaller than omega 2. So the jump of weights occurs really at the first weight. And in this case, the vanishing rate of the fast cycle is just...
Dima, I'm a bit confused about the tangent cone. What tangent cone do you mean? Because the tangent cone always has the dimension of the same, you are in complex case, right?
No. The tangent cone not to X, the tangent cone to the fast cycle. Yes, the tangent cone of X is of course of complex dimension n. Yes, but here we are interested in the tangent cone to the fast cycle. The fast cycle is...
Dima, let's come back to the Kleinian examples, right? If we go to the Kleinian examples, then what does it mean, the tangent cone to the fast cycle?
So, for example, AK, you mean, yes?
AK, yes.
Yeah, so AK, you have here complex surface.
Yes.
Yes. Now you have inside the fast cycle, which means you have a fast loop and it shrinks. Yes, so it is real two-dimensional.
It's one-dimensional, but you can vary this fast cycle along a certain direction, because and you can vary it in such a way that the tangent cone also will vary.
Of course, the fast cycle is not canonically defined. You could shake it a bit.
Okay.
Yes,
Okay.
yes, but I would like to have the smallest representative.
So you just take one representative and
Yes.
you take the okay. Then I'm sorry for the interruption.
So, it's a good remark. So of course everything is defined up to the hornic homotopy, and whenever I can shrink something, I will gladly shrink just to have the smallest representative. So you see, when I specify here the homotopy type, yes, the spheres cannot be shrunk further. So you see, of course, you could pump it a little bit and get a higher dimension, but it's irrelevant. This is the real dimension n-1 is the actual, the smallest possible dimension. You cannot make any homotopy to make it smaller, essentially smaller. Yes, and the tangent cone, it lies inside this half plane. The tangent cone is a subanalytic germ. Yes, of course, we would like to have better estimations, better bounds, but currently this is what we have. And in a particular case, when the two lowest weights differ, the tangent cone will be just of dimension 1, so it will be a half line. And the vanishing rate will be the ratio of two lowest weights. So again, I did not define probably the vanishing rate. It means at which speed the cycle collapses. Yes, precisely at this speed. Okay, so let's see some example. Yes, the very simple example immediately gives you exotic Lipschitz structures. So take the hypersurface. Here it is. Yes, a very simple hypersurface. And then the link in some cases will be homeomorphic to the sphere. Yes, homeomorphic, not necessarily diffeomorphic, yes, because the spheres will be exotic spheres in this case. Therefore, X will be here a topological manifold for such cases. It will be topological manifold, and notice that the equation, yes, the function that defines this hypersurface, it is weighted homogeneous. Here are the two lowest weights, and they differ. Yes, and therefore we get that X has a fast cycle of homotopy type. Here is the homotopy type. Yes. Sorry, in the proposition I forgot to say what is mu. What is this Milnor number? I will tell it later. But in the particular example, mu will be 2. So this is the weight of two spheres, and with tangent cone just half line, and the vanishing rate is here is the vanishing rate. And you see that for different Ds, we will get fast cycles on different vanishing rates. Yes, and so for each fixed n, if we send D to infinity, we will get a countable collection of germs of topological manifolds. Yes, topologically they are all the same R to n, but they are pairwise Lipschitz non-equivalent. And this is a very simple example. Now, in fact, the proposition is known in some cases. For example, for surfaces in C3, this is a preprint by Alexandra. Yes. Now, for R analytic sets, there are very often lots of Lipschitz structures for a given topological type. Yes, for example, for horns, yes, we have countable number of Lipschitz structures. But here we get exotic Lipschitz structures on complex analytic sets, which is maybe more interesting. Actually, it's also not new. So Walter Neumann gave a countable collection of Lipschitz structures, yes, but he used choking horns. And here one uses fast cycle. Yes, so the countable collection with distinct fast cycles, it seems new. Any questions? I have pretty much time here, so maybe I was too fast, too quick. Yeah. So well, if there are.
Let me just interrupt you.
Yes. Yes.
That the point is that when you say infinitely many structures, it's somehow you should specify what do you mean, because that there is this Mostovsky finiteness theorem saying that if you have just something with a limited number of limited degree and limited number of the equations and limited number of variables, then you have just finitely many Lipschitz structures. So then this is so that I would be happy if you emphasize what do you mean by this infinite number.
Yes. So here the number of variables is fixed, it is n, but the degree is not fixed. We play with d. Yes. For d going to infinity. So there is no contradiction, of course, to this finiteness theorem. Yes, for every finite number of degrees, we have only finite number of structures. But as d goes to infinity, we get infinite of them. Yeah, so yeah, so hopefully this clarifies. Okay, so yeah.
Yes, just to mention that Alexandre in the chat comments that the exotic Lipschitz structures is contained in a paper of him with Vincent O'Shea, Don O'Shea Lab in 2014. I think it is the same paper you mentioned, right?
Yeah,
From Walter Neumann is in the page.
exactly. Yes, Yes, with appendix of Walter Neumann, right. Just somehow, as the appendix was attributed to Walter, so I cited him. Yeah, of course, it is a common paper of many authors. Completely right. Yes. Sorry. Yes. Okay. So
one more remark about this paper is that in this paper there are no, let's say, just the fast cycles in the way as you defined it before, because then the cycles were fast themselves, they were trivial, but if you wanted to trivialize them, you had to go quite far. So this was just what you defined in the remark number 4, that it doesn't mean that you have non-trivial cycle, you have a trivial cycle, but if you want it so that it's boundary of something, but if you want it to be boundary, this something that brings it as a boundary has to have a very big size. So this is another kind of the definitions you mentioned that, but it's a little bit different nature. Okay.
So you cannot shrink them hornically. Yes.
Yeah.
Good. So let's proceed. So once again, here I spoke about this proposition, this very special case. Yes. Now let's try to generalize it a little bit. Here we assumed isolated complete intersection. Yes. Now let's try to move to non-isolated case. So suppose, once again, X is just weighted homogeneous. And suppose the intersection with the hyperplane of the lowest weight is a reduced complete intersection, just reduced. Yes, it can have non-isolated singularity. So here is a single locus of some dimension. Let's denote the codimension of the single locus by L, some number. Yes, one can verify. Here are some equations, inequalities, sorry. And then we can extend the very special case to just special case. So suppose omega 1 is smaller than omega L. And here is some technical condition. So when we intersect not with the hyperplane of the bottom weight or the lowest weight, but we move this hyperplane. Suppose this is a smooth Milnor fiber. This is a non-trivial assumption. It is not always satisfied. Then, well, first of all, X has a fast cycle. Its homotopy type is the Milnor fiber. Yes, and actually you could see this Milnor fiber in the previous case. You see the wedge of spheres. This is the Milnor fiber in the isolated case. Now the Milnor fiber could be different, not just wedge of spheres of the same dimension, but it has some homotopy type. The dimension of the fast cycle, here is we have the control, and we cannot improve it much more because Milnor fibers can have different dimensions, different homotopic dimensions in the non-isolated case. And the tangent cone still will lie in this same half plane. This gives you a little bit of control. And still the tangent cone will be of real dimension 1 if and only if the two lowest weights differ. And once again, the vanishing rate here is just the ratio of the lowest weights. So this is the little generalization. And still, this is a special case. Now, just a little remark about the proof, because this will be motivation for the next slide. How does one construct such a fast cycle in the most naive way? Yes. So suppose, well, we intersect X with this hyperplane. Yes. So we move the hyperplane of the lowest weight, move it a little bit. Suppose we have found some non-trivial cycle inside this hyperplane. Well, take the weighted homogeneous foliation. Yes, we are blessed here with the weighted homogeneous germ. So let's use the weighted homogeneous foliation in the most classical way. Here it is. Yes, we have lots and lots of arcs. Each arc either lies inside our germ or lies almost completely outside. Yes, intersects the germ only at the origin. So here is the parameterization of the arc. St is the time, and S1 up to Sn, there are the directions on the sphere, the standard unit sphere. Yes, and then once we have found a non-trivial cycle Z in the section, we will get the fast cycle in this way. So this is sort of horn. Yes, as Z, as we go towards the origin, Z will shrink. Yes, and at the rate which is faster than linear. Good. So this is the idea of the proof. Now the problem is all this was just for weighted homogeneous complete intersections, and very often one would like to have something for semi-weighted homogeneous complete intersections, for perturbations. So the question is how to generalize this proof. This was these were the previous results and the way to prove them. Yes, and the question is how to extend this result to a perturbation of weighted homogeneous germ. Now, perturbations sometimes really change the topology. So let me give some example of what do I mean by perturbation. So let's start from weighted homogeneous germ. Now it has arbitrary singularity, not necessarily isolated singularity. Yes, but say here we speak about hypersurfaces. Hypersurface with arbitrary singularity, and take a perturbation by higher order terms. And the question is how to detect fast cycles on the perturbation. So here's an example. Suppose F is Newton non-degenerate. Yes, which is a rich enough class of hypersurface singularities, and take the Newton diagram and fix a facet. Yes, the face of top dimension. Then the restriction of the function onto this face of top dimension is weighted homogeneous. And then we can present the function as well, it's weighted homogeneous part plus higher order terms. Now you see the restriction to this face, the weighted homogeneous part. In most cases, it will have non-isolated singularities. It will be very often non-reduced even. So this perturbation is quite non-trivial. It is not some equisingular family. Yes, this perturbation, it changes the germ drastically. The question is whether we can still detect the fast cycles on the perturbed weighted homogeneous germ via the initial weighted lowest order leading terms. Yes, and now if you look at the proof, how do we prove it? We need the foliation. Previously we used the weighted homogeneous foliation. Now we have the perturbed germ, and we would like to perturb the foliation. Yes. So the question is, does the previous foliation, which was compatible with some x0, deform to a foliation which is compatible with x? So this is the technical question. Actually, this question is important not just for fast cycles, not just in Lipschitz geometry. Whenever you do something with weighted homogeneous germs, you use this group action or foliation, doesn't matter how you call it, you use this symmetry. And we want to promote this symmetry to perturbations of weighted homogeneous germs. So this question is important. Well, so let's define our players. Well, we have x0. Yes, it is weighted homogeneous germ, complete intersection. Here are the generators of the ideal or the defining equations. Yes, these are some polynomials which are weighted homogeneous. And take the family now. Perturb the weighted homogeneous germ by higher order terms. And we want to deform a foliation, yes, to another foliation such that. So one could impose, of course, many conditions, but let's impose only the minimal needed conditions. So what is really needed? So we want if initial arc sits inside x0, then the perturbed arc sits inside x epsilon. Yes, this is the compatibility. And another condition, we want when we deform, we want that the arcs will not jump. We want the deformation somehow continuous, which means the tangency order or the contact order of the arc and its perturbation will be bigger than 1. So each arc will be perturbed by higher order terms, if you wish. Yes, each arc is tangent to its perturbation. These two conditions, they are the minimal conditions. Yes, this is we cannot give up any of them. Of course, we would like many more, but this is the absolute minimum. The problem is that even these conditions very often are impossible to satisfy. Yes, such a deformation is not always possible. So here is a very simple example. Take a surface, complex analytic surface with isolated singularity. Suppose all the weights are different. Yes, here is I order them in increasing way. And suppose the z-axis sits inside the surface. But when we deform it, the deformed surface does not contain z-axis. Yes, you can imagine many such surfaces. You can write down some explicit equations. Now, what we have here, so take the arc along the z-axis. It must deform to some arc on this deformed surface. But then it will be necessarily of this type with its x component or y component non-zero. And therefore, this arc inevitably will be non-tangent to the initial arc. So you see, already for surface singularities in C3, these two conditions are impossible. And you can imagine, so this is sort of abstraction. You could imagine lots of other abstractions in higher dimensions. Yes, it so happens that all the abstractions are of the same type. So let me define the abstraction locus. What abstracts the deformation of these foliations? So wait. Yes. So once again, we have the weighted homogeneous isolated complete intersection. Take its perturbation. And now we define the abstraction locus. By the way, here I work over real or complex numbers. It doesn't matter. The base field doesn't matter here. So first of all, we take the single locus of our germ. Yes, well, actually, it is the germ has isolated singularity, so this is just a point. Now to this, I add the following. I intersect our germ with the hyperplane of the lowest weight. Here I get some germ, and these could have non-isolated singularity. So I add this single locus, and so on. Then I will intersect with the plane defined by x1 equal to 0, x2 equal 0, and then x1 up to xn equal to 0. All such intersection. And for each intersection, I check the single locus. Even if I start from the isolated complete intersection singularity, some intersections could get non-isolated singularity. And this is exactly the abstraction locus. So the only abstractions to deformation of the foliation sit here. Yes, so and here is the precise statement. So below I will assume that all the weights are natural numbers. Yes, we can always assume this, just scale them. Suppose this abstraction locus is just one point. Then the foliation, the initial foliation of our neighborhood of the origin deforms to the deformed foliation such that, so this is the first condition, an arc sits inside x0 if and only if its deformed version sits inside exceptional. Yes, this is the minimal what is needed. And the deformation of every arc is, let's say, continuous. Yes? So the arc is tangent to its deformed version. And even more, two arcs are tangent if and only if their deformed versions are tangent. Yes? Which is a useful property. And even more, if you take the parameterization of this arc, yes, so we have a function here, a function of t, of s, and epsilon. This is a real analytic function, not just some sub-analytic, Bloch analytic, or Lipschitz. It is honest, real analytic function. And if the higher order terms by which we perturb happen to be polynomial, then this is even Nash function, yes, which is even better. And many other nice properties. Yes. So this is the technical lemma that allows you to deform the foliation when you deform your germ. So once again, when you work with weighted homogeneous germs, you always use this group action, this foliation. And now with this lemma, one can work with semi-weighted homogeneous germs or perturbed weighted homogeneous germs, for example, Newton non-degenerate singularities. You will have a foliation there. Well, some remarks. So the tangency order of arcs is not preserved here, unfortunately. In part 3, we have that two arcs are tangent if and only if their deformed versions are tangent. That's true, but the tangency order is not preserved. If the tangency order would be preserved, then we would get something like by Lipschitz trivialization. And in general, such perturbation is not by Lipschitz trivial. Very often we have the abstraction locus essential, not just a point. Then there is a weaker version of this lemma. Yes, we work outside of the abstraction locus. Of course, we cannot touch it. It's abstraction locus. And then one gets the question, can we use this deformed foliation to trivialize the family? Yes, this is the classical question. You perturb your weighted homogeneous germ by high order terms, and you would like to trivialize. Yes, and I guess there are many people in the audience who did it. Yes, there were many works on this, and well, the answer is yes. We can use this trivialized, this deformed foliation. So here is the theorem. Here I assume once again that the abstraction locus is just the origin. Then the family, yes, the complete intersection is contact-trivializable. And the trivialization is real analytic or Nash outside the origin. More, it is differentiable at the origin. Yes, this seems to be the new result, because until now nobody could get differentiability, it seems. And even more, if we present this trivialization, contact trivialization in the polar coordinates, then it is real analytic also at the origin, or Nash at the origin, which is much stronger. And well, if there is some inequality on weights, then the trivialization is Lipschitz. Yes, if you perturb by higher order terms and the difference yes, the delta of orders is large enough. Then the trivialization is Lipschitz, and if it is even larger, then the trivialization is C1. So part 2 is known. Yes, there were many works on it. Yes, but by part 1 of this theorem seems new. Yes, previously, people always used vector fields and integrated vector fields, and they could not get, say, Nash trivialization, or if I understand correctly, they could not get differentiability at the origin. And here we do get differentiability. So by the way, any questions? Yes, hopefully I'm still online. Well, so this is about the deforming the weighted homogeneous foliation and trivializing the family. This is some inner technical result in our paper, but I think it is important by itself. Well, and for those who have survived until now, so finally we can detect.
Just a moment, could you, I'm reading still the theorem.
Mm-hmm.
Okay. Yeah, it's interesting. Mm-hmm. Thank you.
I will be glad to answer any questions.
We don't have questions, they just understanding the formulation. Okay, thank you.
So maybe once again, in simple words, we have a family, yes?
Yes.
In most cases, it is not Lipschitz trivial. To get Lipschitz triviality, you need to perturb by weights of high enough order. Starting from high enough order, you will get Lipschitz triviality. But if the perturbation is really delicate by low order weights, by terms of low order, then it is not Lipschitz trivial. Still, it is differentiable. Yes, it is not Lipschitz, but differentiable. There are such functions, yes, which are differentiable but not Lipschitz.
Just you remember just what was the result of Alexandra and Maria Parisita on that?
Right, exactly. This is
that you have, or if you have Lipschitz triviality, then you, I just forgot. Alexandra is here, then the Lipschitz triviality implied in their case a differential triviality. Am I right?
I don't know. I didn't know about this result.
Just
also
it is just for deformations, and the result with Alexandre in this case is just for deformations of weighted homogeneous singularities by terms of the same weighted degree.
Right.
I see.
And if it's Lipschitz, then they are already analytically trivial.
Right.
I see. No, I remember. Mm-hmm. Now I remember. Thank you. Thank you, Sidenia.
Okay. Good. So let's move to the last slide, if you have survived. So now we can detect fast cycles not only on weighted homogeneous, not on perturbations of weighted homogeneous germs. I'm sorry, not foliations. Not just on weighted homogeneous germs, but on perturbed weighted homogeneous germs. So once again, I will repeat the setup. We have the germ, a complete intersection. Yes, and there is homogeneity. Yes, it is weighted homogeneous. We have defining equations. Here are their orders or weights. And as in the previous case, I arrange the weights in the non-decreasing manner. And it could happen that several first weights coincide, and then you have the jump. And take some perturbation. And once again, the initial weighted homogeneous germ, it can have non-isolated singularity. Now, suppose the perturbed germ has the reduced intersection with the hyperplane. Yes, it is a reduced complete intersection, as it is written. Well, it is reduced, but still it could have non-isolated singularity. So as before, denote the codimension of this single locus by L. Yes, some number, some invariant. And now we need to ask additional assumptions. So if this intersection has a non-isolated singularity, we should assume that as we deform the hyperplane a little bit, we get a smooth Milnor fiber. This is needed when the intersection has non-isolated singularity. If the intersection has isolated singularity, then this assumption is not needed. And another assumption, when the family is significant, if it is not just a constant family, yes, we assume is bound on the single locus. So you see the initial weighted homogeneous piece, X0, it could be even non-reduced. It could have multiple components. But as we perturb by higher order terms, hopefully we get something which is not too singular. So this is some numerical assumption and a theorem. So if the lowest weight is smaller than omega L, then X has a fast cycle. Its dimension of the real dimension, of course, not the complex, sorry, the typo. Its real dimension is in this region, and I could not be more detailed here because there are different homotopic dimensions of Milnor fiber. And the homotopy type is that of the Milnor fiber. And the tangent cone of this fast cycle lies inside this half plane. And the tangent cone is of dimension 1 if and only if the two lowest weights are different. And then the vanishing rate is at least this ratio. So more or less this is the previous theorem, but now we have it for broader class of singularities. Yes, there are many cases which can be considered as perturbations of weighted homogeneous. For example, Newton non-degenerate germs can be considered as perturbations of some restriction to some top-dimensional phase. Yeah, so this is the result, and well, thanks for your attention.